Welcome to the 6th session of real analysis. In the previous session, we have discussed the algebraic properties of real numbers, and we have seen how we can form root 2, root 6 as irrational numbers. They are not rational numbers. In today's session, we will be discussing more on the properties of R or properties of real numbers, which are namely the order properties of real numbers. So, we can see how the real numbers are arranged. Are they in the ascending order or descending order? Where is the position of 0? Which are called the positive real numbers, which are called the negative real numbers, and so on. So, first definition we will be dealing with is the definition of positive real numbers. A non-empty set P of R is called the set of positive real numbers and satisfies the property that if you have two positive real numbers A and B, the sum A plus B is also in the set of all positive real numbers, and the product also lies in that set. So, that means two positive real numbers when added or multiplied is again a positive real number. Such a set P satisfying these conditions is what is referred to as a set of positive real numbers. If A is an real number, exactly one of the following holds. That means either A belongs to the set P that already we have discussed, or negative A belongs to P, or A equal to 0. That means any real number we choose will be either a positive real number or a negative real number or equal to 0. So, there are only three options for any real number, and hence it is called the law of trichotomy. Trichotomy means three conditions. So, we have the law of trichotomy saying that any real number belongs to either the set of positive real numbers or is exactly equal to 0, or negative of A belongs to the set of all positive real numbers. That means A is a negative real number. If A is an element of P, then A is said to be greater than 0 or A is said to be positive, and if A belongs to the set P union set 0, then we will denote the element A as A is greater than or equal to 0, because it can be possibly equal to 0 as well, or we call A as a non-negative real number. If negative A belongs to P on the other hand, then we will denote it as A is less than 0. This is the mathematical notation for negative of A belongs to the set of all positive real numbers, or we call A as a negative real number. And if negative A belongs to the set P union set 0, then A is denoted as A is less than or equal to 0, or A is said to be a non-positive real number. So, these are the definitions and notations for positive real numbers, negative real numbers, and non-positive or non-negative real numbers. So, using this notation, the law of trichotomy can be written as, the law of trichotomy is A is greater than 0 or A is equal to 0 or negative A is greater than 0, and negative A is greater than 0 is same as the notation A is less than 0. So, this is the law of trichotomy in a more mathematical way. For every real number A belonging to R, either A is greater than 0 or A equal to 0 or A is less than 0. So, this is a very important law that you have to keep in mind. The next result that we have is, if A and B are in, if A and B belongs to the set of all real numbers, A difference B is an element of P is denoted as or denoted using the symbol A is greater than B, or we will say equivalently B is less than A. So, that is the condition for A minus B is positive. And if A minus B belongs to P union set 0, then we have A is greater than or equal to B, or B is less than or equal to A. And if both the conditions hold together, that is if A is less than or equal to B and B is less than or equal to A, then we have the condition that A is equal to B. Then they are exactly the same. The next is a theorem which we have: if A, B and C are in R or are real numbers, and if A is greater than B and B is greater than C, then definitely A is greater than C. So, it is something like a transitivity property or transitivity condition. So, if A is greater than B and B is greater than C, then definitely A is greater than C. And the next result says that if A is greater than B, then A plus C is greater than B plus C for every real number C. Whatever C be positive or negative, A plus C is greater than B plus C. So, let us look at the proof of these two. The first condition was, we were given proof of the first condition. We are given A is greater than B and B is greater than C. So, we have seen the notation A is greater than B is same as A difference B belongs to the set of all positive real numbers. Similarly, B is greater than C means B difference C is also belonging to the set of all positive real numbers. And we have studied in the case of in the definition of positive real numbers, if you have two positive real numbers, the sum of those two positive real numbers is again a positive real number. So, here we have A minus B belongs to P and B minus C belongs to P implies the sum of these two, that means A minus B plus B minus C also belongs to P. So, this follows from where? It follows from the definition. It follows from the definition. So, that implies A minus B plus B minus C can be written as A minus B plus C minus C, that is same as A minus C, because these two add together to form 0. So, A minus C belongs to the set of all positive real numbers. That is exactly what we wanted to prove. So, this implies A minus C is greater than 0, or that shows that A is greater than C. Hence, the proof of the first part. Then coming to the second part, we are given A is greater than B and we have to show that for any real number C, A plus C is greater than B plus C. So, we have A is greater than B is given. Let C be an real number, C belongs to R. So, what is A greater than B means? A greater than B indicates that A minus B belongs to the set of all positive real numbers P. Now, you consider A plus C difference B plus C. What is this? This is equal to A plus C minus B minus C, that is exactly same as A plus C minus B, because we have seen in the previous session that addition is a commutative operation in real numbers. That means, the set of all real numbers satisfies the commutative property under addition, and so we can have minus of B minus C can be replaced by minus of C minus B, that does not matter. So, we have A plus C minus B, which is same as A minus B, and since we already have A minus B belongs to P, we can show that this belongs to P. So, what we have proved now is A plus C minus of B plus C belongs to P, which shows that A plus C is greater than B plus C. So, if A is greater than B, then definitely A plus C is greater than B plus C for every real number C. So, that is the proof of the second part. So, that shows the proof of this theorem. Now, we have the next theorem saying that if A is greater than B and C is any positive real number, because C is given to be greater than 0, which shows that C is a positive real number, then C times A is greater than C times B. That means, this inequality is retained if we multiply with a non-negative or non-negative real number C. C greater than 0 means it is strictly positive, it is a strictly positive real number. So, if you multiply this inequality by a positive real number, the inequality remains the same. And if A is greater than B and if we are multiplying with a negative real number, then the inequality is less than CA is less than CB, or this inequality is reversed. So, these are very known properties, but we are going to prove it rigorously in analysis. So, let us see the proof. Look at the proof of the first part, theorem number 2. The first part proof is like this. We have A is greater than B is given and C is greater than 0 is also given. What we have to prove is CA is greater than CB. So, we start with the given conditions. Given A is greater than B and C is greater than 0. So, what does A greater than B means? A greater than B indicates that A minus B belongs to the set of all positive real numbers, and C greater than 0 indicates that C is also belonging to the set of all positive real numbers. And we have seen in the definition of positive real numbers, if you have two positive real numbers, the product of those two real numbers is also a positive real number. Therefore, C into A minus B also belongs to the set P. C into A minus B also belongs to set P, which indicates by distributive property, you have CA minus CB belongs to P, or in other words, we have CA is greater than CB, as is exactly required in the result. Similarly, we can prove that if A is greater than B and C is less than 0, then CA is less than CB. Let us look at the proof of the second part. The second part shows that you have A greater than B given as in the first case, but C is given to be less than 0. So, C is a negative real number here. So, A greater than B means we have A minus B belong to the set of all positive real numbers. C less than 0 means negative of C belongs to the set of all positive real numbers, because C is given to be less than 0. So, we know that negative of C belongs to the set of all positive real numbers. So, this means again negative C into A minus B belongs to the set of all positive real numbers, which indicates that negative C plus CA plus CB belongs to the set of all positive real numbers, which means CB is greater than CA or CA is less than CB as required in the theorem. So, that is the proof of the second part. Okay. The next theorem is a very important result which shows that if A is a real number and A is actually not equal to 0, then A square is greater than 0. So, if A belongs to the set of all real numbers, and then the square of a real number is definitely greater than 0. Then we have the second result saying that 1 is greater than 0, and third one, if n belongs to the set of all natural numbers, then n is greater than 0. So, let us look at the proof one by one. So, theorem number 3, proof. We are given A is not equal to 0, it should be A not equal to 0 and A is a real number. So, by law of trichotomy, if A is non-zero, then we have two cases. Case 1, A is greater than 0, and case 2, minus A is greater than 0. So, we first take the case 1. Suppose that A is greater than 0. So, if A is positive, so this indicates that A belongs to the set of all positive real numbers. So, we have seen in the definition of positive real numbers, if A and B both belongs to the set of all positive real numbers, the product of A and B also belongs to P. So, we can take A instead of B. So, that shows that A belongs to P, again you take A belongs to P, which shows that A into A belongs to P, which indicates that A square belongs to the set of all positive real numbers. Similarly, if A is less than 0 also, you have negative A belongs to P. So, again you take negative A belongs to P, the product of these two belongs to P, which shows that A square belongs to P. So, that is case 2. So, case 1 is A greater than 0. Similarly, you have the second case. If A is less than 0 also, A square is greater than 0. So, in both the cases, if for any non-zero real number, the square of that number is always positive. So, that is a very important result that you have to keep in mind. So, following this theorem, following this part, we can prove the second part, namely 1 is greater than 0. Why? Because 1 is actually 1 square or it is negative 1 square, and because we have just now proved that for any non-zero real number, the square is greater than 0. So, this shows that 1 square is greater than 0 or minus 1 square is greater than 0, which indicates that 1 is always positive, because 1 is a perfect square of 1 or minus 1. So, 1 is greater than 0. Now, let us see the third part. We have to show that every natural number is greater than 0. So, n is greater than 0 for every natural number n, for every n belonging to the set of all natural numbers. So, the proof is by mathematical induction that we have seen in the previous session. So, first we have proved the first case, 1 is definitely greater than 0, we have proved. Then by induction hypothesis, we will assume k is greater than 0. Therefore, 1 belongs to P and k belongs to P. So, by the definition of P, we have k plus 1 belongs to P, which indicates that k plus 1 is greater than 0. Therefore, by induction, If we have assumed k and proved k plus 1 is greater than 0, by mathematical induction we can show that, or it follows that n is greater than 0 for every natural number. So, the proofs are quite simple, but they are the proofs of very abstract results that we already know. So, that is the speciality of analysis. Now, the next important result that we have is there is no smallest positive real number. If you remember, we had discussed in the first slide in the first class that we will be learning more about real numbers, which is the smallest positive real number, does there exist such a smallest positive real number, and so on. So, the solution of those results can be obtained by studying real analysis, and here is a solution for such a question that we have arised. There is no smallest positive real number. So, we can see why there does not exist such a smallest positive real number is because let us assume that A is the smallest, if possible, let A greater than 0 is the smallest real number. Then we know 1 by 2 is definitely greater than 0. Therefore, 1 by 2 into A is also greater than 0. Why? Because the product of two positive real numbers is definitely greater than 0. But where is this A by 2? A by 2 is definitely less than A. So, smallest positive real number actually, we have to assume that A greater than 0 is the smallest such real number, smallest positive real number. So, now you have A by 2 which is less than 0, but A by 2 is greater than 0 is already proved. So, we have a smaller number which is positive than A. So, which is a contradiction. So, we can similarly find A by 2 greater than 0. So, A by 4 will be greater than 0. Likewise, we can find infinitely many smaller positive real numbers. So, we cannot have such a greater than 0 to be the smallest positive real number. So, that shows the proof of this result. There is no smallest positive real number. Next is a very important result again. If A belongs to R is such that 0 less than or equal to A less than epsilon for every epsilon greater than 0, then A is equal to 0. That means, if we are squeezing A between 0 and any positive real number epsilon, A has no other option, A has to be equal to 0. So, that is this theorem. That is a very important and interesting result. Let us see the proof. Theorem number 4. Given, what is the given condition? 0 is less than or equal to A less than epsilon for every epsilon greater than 0. So, we are given 0 less than or equal to A less than epsilon for every epsilon greater than 0. This is a condition which is given. So, if possible, we have if possible, let A is not equal to 0. Then, because this condition is given 0 less than or equal to A less than epsilon for every epsilon greater than 0, the third condition under the law of trichotomy does not hold here, because negative A, we need not take A is less than 0, because A cannot be negative, because it satisfies this condition given. So, if A is not equal to 0, definitely it means that A is greater than 0. And we have seen in the previous case, if A is positive, then A by 2 is also positive. So, let us take, say, epsilon naught is equal to some A by 2, which is definitely greater than 0. Therefore, by the given condition, what we require is A is less than A by 2. or A is less than epsilon naught, because we are given a condition 0 less than or equal to A less than epsilon for every epsilon greater than 0. But then we will be having A is less than A by 2, which is a contradiction. Therefore, we cannot have A to be greater than 0. So, that forces A to be equal to 0 only, because A cannot be greater than 0 and A cannot be less than 0 as well, because this condition holds. So, it forces A to be equal to 0. So, that is the proof of this result. Then we have the next theorem saying, if A, B or the product of two real numbers is positive, then we should have definitely A greater than 0 and B greater than 0, or both should be negative. So, the proof is again a simple proof. We can see the proof. Suppose we are given AB is greater than 0, then we have to show that either A is positive or B is positive. So, let us assume we are given AB is greater than 0, let A is greater than 0, we are assuming. So, definitely A is non-zero, and therefore, we have 1 by A belonging to the set of all positive real numbers itself. Why? Because if A is positive, 1 by A should also be positive, because if 1 by A is negative, then the product of A and 1 by A is 1. So, 1 will be negative. So, that cannot happen, and therefore, 1 by A should be greater than 0. So, we have 1 by A into AB is also greater than 0, this is given. So, by the definition of P, AB belongs to P and 1 by A belongs to P means the product also becomes greater than 0, which shows that 1 by A into B is greater than 0, which shows that B is greater than 0, because this side happens to be equal to 1. So, we have started with A greater than 0, we have reached B greater than 0 itself. Similarly, we can prove that both should be negative as well. So, the proof is quite similar. So, we are skipping the proof, leaving it as an exercise. Then we have a corollary. If AB is less than 0, then either A is negative and B should be positive, or A is positive and B should be negative. So, again the proof is similar to this one that we have seen here. So, corollary is something like this. We are given AB to be negative, then we need to show that either A is less than 0 and B is greater than 0. So, we assume AB to be less than 0, let A is less than 0, then this shows that negative A is greater than 0 and AB less than 0 shows that negative of AB is greater than 0. So, negative A greater than 0 shows that negative 1 by A is also greater than 0, because the multiplicative inverse of a positive real number is again a positive real number. So, negative 1 by A into negative AB is positive now, which shows that 1 by A into B is greater than 0, which shows that B is greater than 0. So, that is exactly similar to the proof that already we have done. Similarly, we can show that if A is greater than 0, B is less than 0. So, in today's class, what we have discussed is the order properties of R, and we have seen how 1 is greater than 0, which is the smallest positive integer or smallest positive real number, and if at all there exists such a smallest positive real number, and how is a real number squeezed between 0 and any positive real number B. So, that means which is the next positive real number to 0. So, that shows that how close these real numbers are situated. So, these are all following the order properties of R and thank you for today. Thank you.